20 seconds.
A few minutes.
I saw some people grabbing snacks, so just making sure that they get here. Until then, we can congratulate Steph Ortland for defending her PhD, and she has passed. Okay, I guess we can start.
Sure.
Good afternoon, everyone. Thank you for being here on a Wednesday afternoon. It is my pleasure to introduce my friend, Mr. Hamish Prince, or just Prince, for his department seminar. He came here with me in 2021, so fall 2021. He's working with Tristan Lequier on his PhD, and we'll hear some of it today. For his background, he is from a place far, far away from here in a southern hemisphere called New Zealand. Anyone heard? So he's from New Zealand. He did his bachelor's and master's from University of Otago. His bachelor's focused on looking, particularly was geography, remote sensing, and GIS, and glaciology, while his master's focused on looking at atmospheric rivers in New Zealand. After that, he spent some time working with some wonderful scientists at Scripps, UC San Diego, on West Coast US atmospheric rivers and impacts. Got a couple of papers out, and while he's not doing research in his office, you could find him playing Scottish folk music. This is a recent thing with a band called Lockinside, and they play around town in Madison, so go find him there. And his favorite bird from New Zealand is a bird called Kakopa?
Kakapo.
Kakapo, okay, I got it wrong, Kakapo. And with that, we'll give it to Hamish.
Thanks for that, Roger. Yeah, thanks all for coming. This is not a PhD defense or a master's defense, so feel free to ask questions. It's the first time I'm presenting my PhD work to the department. I've done seminars before, but those seminars have been on other research projects, so I'd like to take this opportunity to actually share what I do as part of my PhD. But yes, feel free to ask questions. It's also just exploring this framework that we think about on the 15th floor of considering the climate from its energetic perspectives and all the things that must come about because of that. So here we have the Earth, and if we zoom out, we'll have the sun on the left-hand side, and then we get our solar radiation. And we often think about how important that solar radiation is to our climate system, and it drives everything. All the energy that comes into the Earth system comes from our solar radiation. Things go on in the planet, and then it all exits out again as our outgoing thermal radiation. And this balance must equal, unless we start adding lots of gases into our atmosphere and start changing temperatures, but that's a different story. But today, I'll be speaking a lot about how this energy gets from coming into the Earth to exiting it as outgoing thermal radiation. And so just to start with, if the Earth had no atmosphere or ocean, the surface temperature is defined solely by relative equilibrium. And if any of you have done grants for your radiation class, this will be a familiar idea that if we had no atmosphere, no oceans, no redistribution of heat, the temperature at the surface is solely defined by how much sun comes into the planet and exits. And because we're on a sphere, that temperature decreases as we go towards the poles and our angles increase. And this is what the temperature gradient would look like. We'll be up around 80 degrees Celsius at the equator and dropping down to negative 80 degrees towards the poles. And that's not too different to what happens at the moon. The moon doesn't have an atmosphere or ocean, and that's almost what the temperature gradient would look like on the moon. But we do have an atmosphere and ocean, these diffusive fluids that act to reduce this temperature gradient. And so because of that, the temperatures in our equator are sitting around mid-20 degrees Celsius, and then they drop down to negative 20 degrees Celsius towards the poles. And so because we have these fluids moving about, we move some of this heat towards the polar regions, increasing the polar temperatures and reducing the temperature at the equator. Now, just for fun, what if these liquids were infinitely diffusive? All temperature gradients would be compensated instantly, and this would be the temperature gradient that Earth would have. Of course, we don't live on a planet with infinitely diffusive fluids, and so Earth sits somewhere in between this no transport and infinite transport of our atmosphere has some ability to transport energy around, and so we get that gradient. And this is broadly how the first climate models by Buddyco and North and Sellers and Minabe, they tweaked their climate models by moving the diffusivity of the atmosphere around to equal the temperature gradient of the planet. So back to reality, the temperatures at the poles are much higher due to this continuous heat transport. through. And of course, with increasing temperatures, we get increasing thermal emission, and so the poles radiate twice as much energy than they receive from the sun. So there's a lot of extra energy leaving the polar regions than they receive locally, and that all comes in from transport from lower latitudes. And so the energy exchange of Earth and the poleward flow of heat defines the climate system. We have the surplus of heat in the tropics and the equator, and then in mid-latitude to polar regions, we have this deficit of heat. I'll be talking about these two components here quite a bit. The absorbed solar radiation, so how much sunlight enters the Earth and stays in the Earth. So it's not reflected away, it's how much stays and gets absorbed. And then of course we have our outgoing thermal radiation from the top of the atmosphere, just how much energy is leaving the planet. And so in the tropics we have more energy entering than is leaving, but then of course we go towards the poles and that reverses, more energy leaves than enters. And so this surplus of heat ends up coming over to fill that deficit. We're closing that energy balance. If the surplus didn't fill that deficit, we'll be at an energy imbalance, and that's unrealistic. So those two things compensate each other out. And we've been measuring these broadband fluxes from the top of the atmosphere for a very long time. We've gotten quite good at it. Here's a suite of satellites. You'll recognize this one from the foyer of our building. That's Explorer 7. That had broadband radiometers on it, measuring how much heat left the Earth. Then we had the NASA Irby mission back in the 80s. We currently have the Ceres mission up in the atmosphere on board Aqua and Terra and a few other satellites. EarthCare launched this year. That has a broadband radiometer. And then in the future, there are plans to keep these measurements going well into the future as part of the Libra mission with Peter Pawlowski and Maria Hakuba. And so we're really good at measuring these fluxes. And so we have a long time series of these fluxes from the top of the atmosphere entering and exiting the Earth system. And within the Earth system, this energy can do a lot of different things. It can evaporate water, it can be reflected, it can be absorbed by our oceans, it can melt our snow and ice, it can warm the atmosphere, it can warm the surface, and it can emit and be reabsorbed by different things within our atmosphere. I like to think of it as almost everything that happens in the atmosphere comes from this exchange of energy. And of course, as the Earth warms, the receipt of energy is changing. And so, especially in the polar regions. Things like melting sea ice, changing cloud composition, changing amounts of water vapor, all sorts of things. But these things are emphasized in the polar regions because our warming is the greatest. The poles are warming about 3 times faster than the rest of the planet. And we have dramatic surface cover changes, where we can go from a sea ice covered surface to a non-sea ice covered surface. And that's a big change radiatively. You go from a highly reflective surface to a much darker ocean. So there are lots of different things going on as we start warming the planet that will change our radiative balance. And so this comes to my first chapter, the observed energetic balance of the Arctic and the Antarctic in a warming world. Looking at both poles, this was published earlier this year by Tristan and myself, and this is chapter 1 of my work. And just to introduce you to this annual cycle of the polar energy balance. In our polar regions, they go through this polar day and polar night. So in the summertime, we have constant sun up above, and then in the wintertime, that sun goes below the horizon, and you lose your incoming solar radiation. These two plots have been shifted, so they're centered on when the sun is highest in both poles, which you'll see is the peak summertime in both hemispheres. One just quick interesting point as a side, you see Antarctica gets a little bit more solar radiation. And that's because of the perihelion of Earth's orbit, that during the summertime in the southern hemisphere, we're a little bit closer to the sun. So Antarctica gets a little bit more radiation, but that's just completely beside the point. It's an interesting thing to see there on that graph. And so there's our seasonal cycle of incoming sunlight, and then we have a reflected sunlight, which you'll see is a fair amount, about 50% of that sunlight gets reflected throughout the year for the Arctic and the Antarctic. One thing you can see in this plot is that the reflected sunlight in the Arctic is shifted a little bit further, the peak is further in the year, and that's due to the loss of sea ice over the poles. Over the Arctic, especially later in the season, whereas Antarctica stays as a big shiny white surface, and so you don't get that drop-off of albedo, of reflected sunlight, as early in the season as you see in the Arctic. But then adding that thermal emission plot on, this comes to this idea of, you can see in the wintertime our solar radiation drops right down, but we still have a lot of thermal emission. We have so much more thermal emission in the wintertime than sunlight absorbed. So of course, we have energy either being stored in the system or being transported into the polar region to then cause this emission, because it's certainly not coming from the sunlight during those months. And then one thing I'll talk about a wee bit in this talk is the clear sky signal. And so these sort of lines have been in the all sky, and so it's looking at if there's clouds and if there's not clouds. It's just every day of the year, look at the Earth and what is the emission. But we can also say, look at the Earth when there's only clear skies. Look at the Earth when there's no clouds around, and what signal do you see? And so this is where the surface impacts really stand out. And so you can see here, the drop-off in reflected shortwave radiation is a lot more prominent when you look at clear skies. Clouds aren't playing a picture here. We're only looking at changes in the surface properties. And of course, when you start losing that sea ice later in June, July, August, that drops off much quicker. And you don't see that change in Antarctica, of course, because it's a big shiny continent that's not losing its sea ice over that summertime as much. And over the last 20 years, we've seen dramatic changes in our sea ice cover. Here is the seasonal trend you see here, and in the lower plot here is the annual mean sea ice cover in an area of millions of kilometers squared. You can see both regions have significant seasonality coming in and out, but over time we're seeing this loss of a few million kilometers area of sea ice cover. In Antarctica, the story isn't as simple. For many years, it didn't look like it was changing, but in recent years, especially 2016 and 2017, there were dramatic losses of sea ice around Antarctica. On the same order, you can see the range of this graph is the same for both of these plots. It's on the same order of magnitude as loss that's happened over the Arctic over a much longer time. And so we're seeing these changes in sea ice cover on the same order of magnitude of both poles. And so this comes to the question of how has the polar radiative balance changed over this observation period using observations from the Ceres mission 2000 to 2020. We don't use early missions because they're not as well trusted. The Ceres mission has really strong, really good calibration through time. So we know that those sensors aren't changing through time, and so looking at these trends from those sensors is a really robust way of measuring these things. Just a quick note how I define my polar regions here, because it's not as simple as the Arctic Circle. So often the Arctic Circle is, well, it's defined as a 66 degrees north circle around the polar regions. But you can see sea ice, especially over Antarctica, extends well beyond that 66 degrees south. And so if I define my polar region by 66, you wouldn't capture changes in sea ice far away from that area. This red line is the max extent of sea ice for each area. And then also in the Arctic, there's this big swath of the North Atlantic over Norway that doesn't get any sea ice. And so we don't really want to include that area because that's not what we're trying to see here. And so we define our polar regions as where the mean of temperature is below freezing. And you can see that really nicely outlines where our sea ice cover extends out to, especially in the southern hemisphere. We capture this full region, and the blue is what we're studying, and that red is the max extent of our sea ice. And so that's the polar region that's looking at. Jump on. So here's our Arctic graph. For 20 years, it's mean annual sea ice at the moment, so it's showing a green line. We'll build this graph up. And so you can see over these 20 years, sea ice has declined by over 1 million kilometers squared. And then we can put in our solar radiation. So absorb solar radiation. If it's red, we're absorbing more solar radiation. And if it's blue, we're reflecting more solar radiation. It's the anomaly of solar radiation here. And as you can kind of see here, as sea ice is low, solar radiation gets more absorbed, especially in these low years. 2012 was a low year of sea ice, and then 2016 was another low year of sea ice. You can see we have high absorption of solar radiation. We can check a trend line on that. It's looking pretty positive. We can also look at this during clear sky. And so, again, it's this idea of look at the polar region when there's no clouds around. Surface impacts become more important, and you can see that the trend is quite a bit more stronger. That the years with low sea ice have a lot more absorption when there aren't any clouds around. But the important point to see here is that when we do consider clouds, there is still a trend. There has been some arguments in the last few years that maybe clouds will completely mask the reduction of sea ice. You reduce the sea ice, maybe clouds will fill in that space and leave the Arctic with the same albedo. Yes, they do mask that trend, but that trend certainly still stands out. You still have a signal of sea ice loss when you do consider clouds in the region. They're not masking that loss of sea ice. And we can put those trends up there on top of at the moment. We can move on to look at the thermal emission. And quite nicely, that thermal emission is also increasing in a very similar trend to the solar absorption, responding in similar ways to sea ice loss. Through there. So yeah, clouds only have a very small impact on the trend. But interestingly, for the thermal emission, Yeah, for the thermal emission, it's much smaller than the impact on the solar radiation absorption. And so that's telling us when we consider clouds or no clouds, the Arctic is warming in a very similar way. Moving over to Antarctica, it's a bit of a different story. You can see this green line here is our sea ice again. And in 2016, that collapsed down, and we had a lot more thermal absorption, solar absorption, sorry. And we do have a bit of a trend going on. Of course, looking at this plot here, adding a linear trend line to this is a bit silly, and there's certainly arguments to say that from 2016 we've almost shifted into a new regime. There's been a bit of a step here, and so adding a trend line to a plot like this isn't too insightful, but maybe we should have a flat line here and then we have a new line here. We've entered this new state of Antarctic absorption as we shift into this dramatic loss of sea ice. But the important point is you don't see a response in the thermal emission. That thermal emission is pretty steady. In fact, it's almost decreasing in the trend there. When you have these big losses of sea ice, a lot of solar absorption, but you only see a small response in the thermal emission. It's pretty interesting. Put those two next to each other. In the Arctic, you've got absorption of solar radiation and increase in thermal emission. In the Antarctic, you see that solar radiation is responding to our sea ice loss, but our thermal emission is not responding. And so we can look at it with a bit more statistically and show these scatter plots. And so these are annual accumulations of thermal emission and solar absorption. Think about it, you're looking over the Arctic, and over the course of the year, how much total energy comes out of those regions. In the Arctic, it's quite a nice relationship. It's about 2/3 of the variance of our outgoing long-wave radiation can be described by how much short-wave radiation gets absorbed. That seems intuitive, that if you absorb more solar radiation, you end up with more thermal emission coming back out. And I've colored these dots by the mean annual sea ice area. And so you can see when the dots get lighter, you've got less sea ice, and those are the years that you have more solar absorption and more thermal emission. And so we go from dark to lighter spots, and also as short-wave radiation increases, so does thermal emission. Nice. That meets our expectations of our ice albedo feedback. Coming into Antarctica, it's not as simple. Our R squared drops right down to below 0.3, and so less than 1/3 of the variance of OLR can be described by our solar radiation. So you can see here, as solar radiation changes, the OLR is much less responsive to that change. Looking at the clear sky, it's even more of a stronger story. When you look at the clear sky Arctic, that R squared actually increases, and you get a much closer, or not much, a closer relationship to shortwave radiation. But in the Antarctic, it almost looks like OLR is unresponsive to changes in shortwave radiation when you look at it without clouds. So, and we know that sea ice has been changing. These colored dots show changes in sea ice area at the surface. And we can see there that as sea ice reduces, you definitely absorb more solar radiation into the area, but it's almost unresponsive from the OLR. You move along this plot and it's not changing at all. Interesting story that's coming out of this. We can look at it spatially to try and see where these things are going on. On the left-hand side, I've got this sea ice cover, and this is shown in days per year. So where it's white is where we get 365 days per year of sea ice cover, and as we go down to the pinks, we drop down to 0, which is our 0 days of sea ice cover for those regions. And then down below that is the sea ice trend. And so where it's blue is where we're losing days of sea ice, and so where it's that dark blue, 6 days per year of sea ice loss. So for each year, we lose 6 days of sea ice, and there's the blue areas. It's one way to read that graph. And then over here, we've got our Arctic solar absorption trends. And of course, where we see losses of sea ice are exactly where we see more absorbed radiation. We can overlay that plot over there as well. You can see that less sea ice is where solar radiation has been absorbed, which is exactly what we'd expect. Coming through the thermal emission, you can see this is much more dispersed across the entire Arctic region. It's not nearly as concentrated as solar absorption, but it's still increasing statistically significant. And should put those two next to each other. We've got increasing solar absorption over the Arctic, and we've got increasing thermal emission. There are areas over land where we also see increasing solar absorption and emission. This will be associated with changes in snow cover, as we'd expect. If you lose snow cover over Siberia, you change the albedo, you absorb more radiation, and that comes back out as thermal emission. Over Antarctica, this gets interesting. Coming back to here, there are places in Antarctica that have increasing sea ice cover. Over here in the Amundsen Sea, this is associated with the movement of the Amundsen Sea low, moving sea ice around. And so you have reducing sea ice cover over here in the Ross Sea, and as you come over, some of that sea ice has been affected into these regions. And you get these little spots of increasing sea ice cover. And we see that in our solar absorption trends. Over here in the Ross Sea, we have vast increases of solar absorption. We're losing sea ice here, we're increasing that solar absorption, we're gaining sea ice over here, and we're reducing our solar absorption. And same in the lee of the peninsula as well. You can see that's a region of reducing solar absorption. And that's exactly where we see increase in sea ice cover. But we also have these vast areas where solar absorption is occurring more and more in the last few years. Just to overlay that plot there, you can see that exactly lines up. Thermal emission, nothing's changing. If anything, in the clear sky, Antarctica looks like it's cooling. So the spots here shows statistical significance, and a negative trend in thermal emission shows that regions of Antarctica might be having a reduced thermal emission, which is pretty interesting. But importantly, we don't see increases in temperature in the clear sky or with clouds of that solar absorption. So where is it going? That's just to compare you back to the Arctic plot. You can see we definitely don't have compensation from our solar absorption to our thermal emission. So where is the energy going? We can look to our oceans. This might help us explain this. Over the Arctic, we know that sea surface temperatures have been rising. It's been about 1 degree Celsius over the last 2 decades. This is summertime peak monthly sea surface temperature. You can see that's increased pretty steadily over time. Interestingly, the ocean heat content in the Arctic Ocean hasn't changed that much. This does come from reanalyses, just to make a key point of that. We're getting lots of increase in the sea surface temperature in the Arctic, but not much increase in the ocean heat content. But if we put Antarctica onto this plot, you can see what's going on. Southern ocean heat content has increased significantly over the last 20 years. There have been vast increases in southern ocean heat content, but barely a change in the sea surface temperature around Antarctica. And that kind of just tells us the answer to the story straight away.
Where are you getting measurements of southern ocean heat content?
So this comes from the OS5 ocean reanalyses,
Yeah.
which takes in a whole bunch of things, but that's a good point that this is a reanalysis, and I do touch on that later on. But from a reanalysis, as a first look, it looks like this answers that question. In Antarctica, the heat has all gone into heating the southern ocean, but not the surface. In the Arctic, the heat is going to warming the surface, which then can be emitted as thermal radiation that we can measure from space. And we get this picture here, that we can describe the Arctic as a shallow bathtub. The energy comes in, it warms the surface within a year, and comes back out again. And so we get this trend of about 1 watt per meter squared per decade of increasing solar absorption and increasing thermal emission. It looks like it's compensating at South Wales. A shallow bathtub, you warm it up, you can feel the heat off the top. But in Antarctica, we call it this energy sink, that you can send the energy in, and we are increasing it a little bit in our solar absorption, but that heat is being put somewhere else that is not coming back out as thermal emission, and it's being taken up by our southern oceans, is the idea that we're proposing here. And this is not a new idea. There's been a bunch of papers. Here's Kyle Lama from Washington. He's shown modeled plots like this that show, yes, the Southern Ocean has very little surface warming. You can see that as the blue line here. Here's Antarctica. Here's our latitude cross-section. But the Southern Ocean original overturning is upwelling cold water against Antarctica, and then it's subducted down towards the equator. So heat is preferentially stored where surface waters are subducted to the north. And so if you have this overturning circulation, and you start absorbing heat up here, that heat is going to be dumped down into your subsurface closer to the equator. And so it's not locally stored. The heat is going within the Earth system, but it's being stored somewhere else that is not visible from space. We're not seeing the imprint of this thermal emission from space. It's been taken up by our Southern Ocean heat uptake. And here's another more recent paper, just showing that heat storage rate is increasing around Antarctica. So this red shows that for each year, we have more and more heat being taken up by the ocean, Southern Ocean, but we're also seeing increased heat transport rates towards the equator. And so combining those together, you get your sea surface temperature trend. You can see around the world, most of the places have increasing sea surface temperature. Draw a line at 45 south. You don't have changing sea surface temperatures around Antarctica. You even have decreasing temperatures on the ocean from their results around Antarctica. And now both of these were modeled results. We don't have good observations of the Southern Ocean. It's very hard, there's ice around, it's hard to get there even. So both of these come from highly idealized, well, not highly, from modeled results from ocean reanalyses and objective analyses for the case of here. And so making oceans is hard, but we show through top of atmosphere robust observations that this idea agrees well with what is happening at the top of the atmosphere. That the changes in the radiation on the top of the atmosphere agree very well with these concepts. That the energy has to go somewhere. We looked back a few years, there's a paper by Kyle Lama that shows I know where the energy is going, and the ocean reanalysis is telling me that. And so we started to develop this picture with good reasoning from other results that our observations are meeting the expectations of these models. So sweet, we're happy describing Antarctica as an energy sink. Onto the Arctic. The story seems simple, but is it too convenient is an interesting thing to consider. The ice albedo feedback in the Arctic is pretty well known. We know that you reduce ice, you increase solar absorption, you increase temperatures, you melt more ice. It's a local feedback, and lots of people describe it. We know the Arctic is a shallow mixed layer, that any heating at the surface is not taken into the deep Arctic Ocean. It's pretty stable, shallow mixed layer, not much going on. We know that heat is re-emitted later in the season. These come from buoy observations and lots of other ship tracks and things in the Arctic. And we know that heat absorbed by the Arctic Ocean does come back within a season. And we also know that sea ice is predictable. If you know the temperature of the Arctic Ocean early in the season, you can predict how the sea ice evolves later on. And so for all these reasons, we might think that our story makes sense. That solar absorption warms the surface and emits back that thermal radiation back to space. But of course, here are these remote mechanisms. Non-polar circulation changes, but then also transport of moisture and heat into the Arctic region, which we're not considering here. One key point is that we only present a snapshot of our current climate, which is in a transient period at the moment. We're not in an equilibrium climate. It's just one thing to consider going on. So yeah, could non-local influences reproduce these findings? And the key point is what controls thermal emission in the Arctic? We know that solar absorption through sea ice loss is well accepted. What influences thermal emission? Is it solely surface temperature? The answer is no. Things like atmospheric temperature, cloud top temperatures, cloud phase, atmospheric moisture at different altitudes, atmospheric chemistry, greenhouse gases, and surface emissivities all change thermal emission. The atmosphere is fairly opaque to thermal emission. There's no reason to expect that changes at the surface completely change the top of atmosphere emission. And what I've shown here is a spectra of thermal emission. This is just over the Earth in a total. When the black line meets up with the red line, that's emission from the surface. That's our window channels, 11 microns we can see down to the surface. But as we go into our further wavelengths, we get our CO2 band and we get water vapor continuum coming into this, that our emission comes from different levels in the atmosphere. So say we start changing our surface temperatures, we'd expect that to impact our emission spectra through here, but there's a whole swath of our thermal emission that is not coming from the surface. And so maybe our understanding is a little too convenient that are changes in this part of the spectra that sees down to the surface what's going on, or are we warming the entire atmosphere over the Arctic and the full spectra is changing? Or is water vapor changing and compensating what might not be changing at the surface? Lots of questions. And so much of we try to study processes that impact Earth's spectra of thermal emission. That would be a pretty good idea. It turns out there's a team on the 15th floor who are doing just that, studying the spectral thermal emission of the Arctic. And this is the pre-fire mission that launched earlier this year from New Zealand to study exactly these processes with a focus on the polar regions. We'll just watch this launch. It's from Mahi in New Zealand, launched by Rocket Lab. Second stage comes off. So these are two CubeSats that are now orbiting Earth. I can see the team at the back there. Here's pre-fire, launching out. So these satellites are measuring the spectral emission of Earth. This particular focus on what impacts the different wavelengths. What changes in the atmosphere, what changes in the surface, how important is changes in the surface temperature to the top of atmosphere thermal emission. You can see a lot of our other sensors that spectrally resolve the atmosphere don't reach out that far, they get up to 15 microns. The series data, which we've been using this whole time, that's a broadband, so it samples the whole spectra as a whole number, but pre-fire for the first time breaks that down into about 50 spectrally resolved channels. So hopefully, over the course of this mission, we can get some idea of how important is changes in surface temperature or changes in surface emissivity or water vapor presence in the atmosphere. is it changes in water vapor that is compensating changes in solar radiation? It's a big unanswered question that we want to get into. So there's lots of science questions to answer there. But this is on a pre-fire science presentation. Come back in a year or so for one of those. So we'll move back to my work here. We've just made some pretty interesting conclusions from observations of the polar radiative balances. These are observations, these are true. These are top of atmosphere observations of what's going on. We've tried to describe those with our surface impacts. We've been fairly successful in understanding maybe where our Antarctic energy goes, and we've opened up questions of can the Arctic change be explained. But I have these other arrows on the plot, which are equally as important, and that's our transport of energy into the regions. And in submission, a reviewer asked a question that we also had: can you utilize observations of poleward energy transport to close this energy balance? All of this should cancel out. The amount of solar radiation coming in and the amount of thermal coming out should be balanced by how much comes in from the atmosphere and also from the ocean. Could we change it? Could we close it? And so we get this question. Observations of poleward energy transport. It's a tricky thing to think about. Poleward energy transport, let's just talk about this for a second. It meets 3 requirements. It's consistent with all these ideas. It must close the energetic balance, as we talked about before. The temperature and the exchange of energy is closed by how much energy is sent poleward. Without that, our temperatures would be vastly different. It also meets diffusive requirements of the gradient of energy. And so if you consider this as like gradients of energy, the amount of energy that must flow from here to here has a theoretical diffusivity that must meet that. But it is also the net result of dynamic mixing and moist static energy, which is all of the dynamics in the atmosphere. The circulations we see, the movement of energy, the movement of moisture, our atmospheric dynamics must exactly balance our energy balance of the atmosphere. Let's just cut this one out because it is theoretical. There isn't a single diffusivity of the atmosphere. There are so many different geophysical processes going on that do have different diffusivities, and so you can't really approximate the atmosphere from a purely diffusive perspective. But these two certainly balance out. From a dynamical perspective, you can think of atmospheric heat transport as the poleward wind of our total energy. Just breaking that down a little bit more, you can think of it as the meridional wind of our moist static energy, which I've plotted here from Euro 5, moist static energy in the background, and just a random months meridional wind. And you just multiply that together and you get an advection of heat poleward. Breaking it down mathematically is not too tricky, but it's got a bunch of zonal means and zonal anomalies, but it's just your meridional wind times by your moist static energy. And you can break it down by transientities and overturning and things. And this is how AHT is calculated in the vast majority of studies. If you read any paper on atmospheric heat transport, they do this. They download their reanalyses, they multiply their moist static energy by the poleward wind flow, and you get how much energy moves towards the poles. But what is a reanalysis? It's a magical website that gives me all the data I want. But it's a blend of observations and Earth system models to provide complete continuous data sets. It uses physics to fill in the gaps between observations in both space and time to calculate new variables. So it takes in the observations, which are imperfect, it runs a bunch of physics to give you complete outputs that you can then nicely manipulate. But reanalyses are not observations, and they're not constrained by energy conservation. It's a really important point. That they often do unphysical adjustments through the data assimilation process to match different time steps. So say you had one state of your reanalyses and it runs the physics forward, and then it gets a new observation that's slightly different than what the physics ran forward. Now it has to jump to a new state. That's a change of energy in your system. Say it just has to remove a bunch of moisture in a certain grid cell, you're not conserving energy at that point. There's reasons to not believe that reanalyses provide good representations of energy, especially things like water vapor and precipitation. Reanalyses do not do well in representing the true nature of precipitation on our planet, and precipitation, of course, is movements of moisture, which is the transport of energy. So we've got reasons to not believe reanalyses are doing well with energy transport. And there was a grad student from University of Washington, Tyler Cox. This year he published this paper on trends in atmospheric heat transport from reanalyses from atmospheric models, but then also from full coupled CMIP models. And what he shows is that over the last 40 years there is quite some disagreement between these products. That in the tropics, reanalyses say positive heat transport is to the north and negative heat transport is to the south. And so when you look at this plot by the side of the equator, reanalysis say that poleward heat transport is vastly increasing in your tropical circulations. That your tropical overturning is increasing dramatically and seeing a lot of heat poleward, but in your coupled climate models, that's not going on. It does better in the mid-latitudes, like in the southern hemisphere. Mid-latitudes, all products suggest that poleward heat transport is increasing, and that's a pretty robust trend that we understand is increases in any kinetic energy circulations in the southern hemisphere. But what's going on here? There seems to be some disagreement going on. And wouldn't it be great if we can add a plot of observations to this line? So let's just talk about the energetic perspective. Well, before I do that, one quick point is that you can't do this from observations. We don't have observations of moisturistic energy through the entire atmosphere vertically integrated, and we don't have good observations of meridional wind through the entire atmosphere. That is a very hard thing to do that we don't do well. And so you cannot observe the dynamic perspective of atmospheric heat transport. It has to be done from a reanalysis. But, as you might expect, from the energetic perspective, things are a bit more promising. If you consider the atmosphere from the top of the atmosphere, all you have is incoming solar radiation and outgoing thermal emission. You plot that on a graph like this, Antarctica to the Arctic, the equator in the middle, you have that curve of incoming solar radiation and the thermal emission going on. So positive is an increase, and that's the deficit. You add these two together, you get this plot here, the surplus and the deficit. And like I described at the very start, this surplus must fill these deficits to close the energy balance. And if you simply take the integral from this plot here, you just sum up every bin from there, going up, you can accumulate your energy transport. So you just take your line and you integrate from one pole to the other pole, you end up with your top of atmosphere energy transport that must be going on. Negative transports to the south and positive transporters to the north in this perspective. Can we do that for the atmosphere? You need to define both your boundaries. So your top boundary of energy loss is your radiant balance. That's nice and simple. At the surface, you have your radiant balance, and then you also have these other fluxes of heat into the atmosphere, your latent and sensible heat fluxes. When we put that onto our graph, we see we still have a big thermal emission of the atmosphere. That's our loss of energy. We have our solar absorption in the orange there. And then we have this latent heat flux, that green. There's a huge amount of energy being added to the atmosphere from the surface. The evaporation and condensation of water in the atmosphere adds so much energy to our atmosphere. And then you can see there that sensible heat flux is a small amount of energy, but adding to the atmosphere. You sum all those together, you get your surplus and your deficits. Just like from the top of the atmosphere, you still have this gradient in energy from the equator to the poles. Again, you integrate from one pole to the other pole, and you end up with your atmospheric energy transport from an energetic perspective. Importantly, this can only be done on zonal means, but there's a constraint that you don't have energy flowing through your polar regions. Polar regions are a cap, and there's no energy being lost out of that polar region. It must come from where we have energy available. That's what the math looks like. So we have our radiation, our sensible and latent heat fluxes, and you integrate it from one pole to the other pole, from Antarctica northwards. But there's an extra term, the storage of heat. And this came up in Emily's talk last week. The tendency of the fluid itself to store heat is a loss of energy or a source of energy. And so you need to consider that storage. It's not shown here because it's not an energy balance term. It's a loss of energy to the change of the change of temperature of the fluid here. And you include moisture, and so it's almost like a time derivative of moisturistic energy is one way to think of that. And so you need to consider that. But again, there's that pesky moisturistic energy which we can't observe. I'll come back to that. So yeah, what can we observe? We can observe radiation pretty well. How about our turbulent and sensible heat fluxes? If you went to Emily's talk last week, you'll know that's pretty hard to do, even from a single station. And I'm not the first to ask this question. Turbulent heat fluxes are hard to measure. They require eddy covariance techniques to measure directly, and that involves single towers to be installed in an environment. So do we have any hope of measuring global turbulent and latent heat fluxes? If you read any Trendworth publications over the last 30 years, the answer is no. Their global estimates of surface fluxes have systematic errors. We don't sample them well enough. There's too many uncertainties. It requires parameterizations and unrealistic coefficients. And so that sort of led the community to only use reanalyses for calculating these fluxes. But can we use observations? And it turns out over the last 20 years, we've done some pretty good observations of these things. If you use a microwave sensor, you can get things like a temperature gradient at the surface, you can get a humidity gradient, and you also get a surface wind gradient. And with those three things, you can parameterize your turbulent and latent heat fluxes. If you blow wind over a humidity gradient, you can estimate how much energy is being evicted vertically from that latent heat. And same with sensible. If you know your surface temperature of your ocean and your 2 meter temperature, if there's a gradient of temperature there and the wind blows along, you're mixing that temperature up into the atmosphere. And this can be done solely with microwave sensors, passive and active, so scatterometers and radiometers, but there's been a bunch of them up there and they're going to be up there for a long time into the future.
They measure all those quantities? The 2 meter temperature and the 2 meter humidity
Yeah,
is
you
measured
get-
by active and passive microwaves?
You get moisture, near surface moisture from microwave sensors.
You sure it's not over a deeper layer?
Definitely the wind comes up over a deeper layer, but near surface humidity you can get.
Okay.
And yeah, a bunch of organizations have devoted a lot of resources to develop these estimates of global heat flux. And these are some of the 5 that I'll be using in my work. At NASA, there's a product called C-Flux. At Woods Hole, they've got this away flux. The Japanese have J-Furrow from Germany, and Max Planck, they have HOPS, and the French have iFramer. And these come from, big ocean communities that want to understand ocean turbulent heat fluxes, because that's really important when you look at things like ocean heat uptake and water mass transformations and things like that. And just to compare them back to reanalyses, it looks like these observations are doing better. And so this is just a comparison back to a bunch of buoys around the ocean, where it's more red, the mean difference, the error is greater, and when it's more blue, the error is lower. And clearly, when you look at MERA 2 and JRI 5 and ERA 5, you have these yellows and greens and reds even, showing that you have pretty high difference from the reanalyses compared to these buoys. But when you consider these observations, primarily from satellite perspectives, that error seems to be reduced across a lot of these products. So there's evidence that maybe we're doing better at measuring our surface heat fluxes, especially our turbulent heat fluxes, than what may have been thought of in the past. And so this comes to me, chapter 2. I'll run through this fairly quickly, but this idea of can we constrain atmospheric heat transports from observations of Earth's energy balance. This is what's currently done. What I'm saying is, let's come over into the energetic perspective and take our observations to get observed atmospheric energy budget, integrate that across to get our AHT observations, and compare that back to all our different ways of getting atmospheric heat transport from reanalyses. Of course, you can also do the energetic perspective from reanalyses. You can take out your radiation, your turbulent heat fluxes from ERA 5, calculate a budget from ERA 5, and get your energetic AHT. I've got this atmospheric energy dependency. That's the tendency change over energy of the fluid. We can't observe that, so that has to come from a residual from these products. And that's one thing that ties it all together. Maybe we can try and avoid this in the future, but at the moment we can't observe those, and so that must come in as a correction. But importantly, this comes out as 0 in the annual mean. The amount that your atmosphere heats and cools over the course of a year averages itself out. Of course, on long time scales, that's not true. We have a warming of our atmosphere by global warming, but in the annual mean, the amount we heat and the amount we cool by equals out pretty evenly. And so here's our sensible and latent heat fluxes in the annual mean. And you can see, compared to ERA 5, they're a bit higher in the higher latitudes. And in the southern hemisphere, there's a bit of uncertainty of where they should sit. Some of them even say we have negative sensible heat fluxes in the Southern Ocean, which is would think to be incorrect. And then when you look at the latent heat, you can see the order of magnitude here. Of course, latent heat has a lot more energy to the atmosphere than our sensible heats. And they both get it pretty accurately, but ERA 5 suggests there's a bit more energy input from latent heat than the reanalyses. When you combine that together, you end up with your total turbulent heat flux. Observations say there's a lower heat flux into the atmosphere in the tropics, and then as you go into the polar regions, it flips around. The observations say there is more energy going into the atmosphere. And so broadly, we have a shallower gradient of energy entering the atmosphere from our turbulent heat fluxes. Combine it all together into our atmospheric energy budget, and then you take the area weighting of that, and you get this plot of how much energy the surplus and the deficit. And of course, we can integrate from one pole to the other pole to get that gradient. So there are differences in the budget to start with, but when we come through to the heat transport, this is the big pot we get. Southern Hemisphere, we get nice agreement. Almost all products, so the dotted lines are reanalyses. We've got ERA 5 in 2 different ways. We've got ERA 2 and JRA. all in the dotted lines, they overlap each other pretty nicely. They all agree with each other. And even error 5 from the energetic perspective, which I showed before, that matches it as well. So this shows us that like error 5 is fairly consistent with itself. That the exchanges of radiation within error 5 are pretty consistent with the movement of energy by dynamics within error 5. So we're happy with that. When you put the observations on, southern hemisphere they agree, northern hemisphere they don't. And this is kind of interesting because the observations tend to cluster together compared to the reanalyses. And so maybe we could ask the question, are observations capturing the real world and for some reason reanalyses are doing it incorrectly? There are a few hints that we can look at to know what is true about the atmosphere that give this away. And one of the big points is the equatorial energetic crossing. And so the amount of energy that crosses the equator defines the location of the ITCZ, which we know pretty accurately where that is. And so if you end up sending more energy across the equator, you shift the location of the ITCZ. And you can see all the reanalyses tend to agree about 8 degrees north is where you cross the equator, but some of the observations shift that quite a bit further north or further south onto the equator. And so already we know that that's can't be true because that would shift the position of the ITCZ to somewhere where it's not realistic. And so there are hints about the Earth system that we can use to assess how correct these products are. So maybe all the observations are getting things wrong and the reanalyses are more closer to reality. But it's interesting that in the southern hemisphere you don't get that difference. Breaking it down seasonally, the only thing I want to show here is that that difference pops out in the summertime for the northern hemisphere. April and June is where you get that difference. They start to diverge. And in June you can see this flat line here. So the observations say there's no northward heat transport in the northern hemisphere summertime, which seems incorrect. That all the heat is being sent to the south, and because this is zero, it's saying that there's no northward heat transport in the northern hemisphere summertime. So maybe reanalyses aren't doing it quite right.
You mean observations?
Yes, observations.
And so those are those retrievals of the turbulent fluxes. That's where the observations are going on.
Yes, and so I don't show it here, but we use the series observations of radiation, which agree well with reanalyses.
Okay.
And so the difference that comes across, especially when you look at like the error 5 product, the radiation is identical between the two, basically. And so
Okay.
all the difference comes from where your turbulent heat flux comes from.
So maybe we don't observe 2 meter
Maybe we don't do it
moisture
well enough.
and temperature?
That's a good point. You can look at the seasonal, similar idea. If we plot these on a graph and color it together, where it's green is southward transport, where it's pink is northward transport. You can see wintertime, peak transport to the north, and then wintertime, southern hemisphere, peak transport to the south. But you can see the change in color. That in the reanalyses, you have continuous heat transport in the northern hemisphere over the summertime, but that drops out in your observations. And so there are some clear differences. Southern hemisphere gets it quite nice. It's fairly similar, but northern hemisphere you can see that difference. And it's just interesting that all the products disagree in the same place, that summertime northward heat transport is not accurately represented in our observations. That is assuming that this is reality, which is a big assumption. We can look at the time series. This is a pretty messy plot, but if you just plot it all on a single latitude time series, the energy budget and the monthly transport, it gets a bit messy and you can plot out the correlation. But if we flip that around to look at the zonal mean correlations, this is the correlation of heat transport for each zonal band. It's just how much in agreement are the products through time in their monthly anomalies. And so you just look at these dotted lines to start with. That's the reanalyses. They agree pretty well in the latitudes. That's a 0.95 correlation between the two of them. But in the tropics, even the reanalyses start to disagree with each other. So when you compare error 2, this is comparing back to error 5, you can see that there's a big difference in the monthly variations of northward heat transport. And that's due to the representation of tropical precipitation. If they do that differently, they'll start exporting different amounts of heat out of the tropics at different times. And so even between reanalyses, they don't agree with how much moisturistic energy has been sent poleward in the time series anomaly. When you look at the observations, you get a reduced correlation. It's still quite high. This is around 0.7, 0.8 for a few of them. But then again, in the tropics, we drop right down to a below a 0.4 correlation for most of those observations. You can also compare it back to one of the observations. So this is an observation product, C flux, compared to all of the others. You can see it's almost the same thing in reverse. All the observations tend to agree with each other, and then you get your reanalyses disagreeing, especially in the tropics. But certainly in the mid-latitudes, there appears to be some level of agreement between the two of them. I'll just skip this plot, don't need to show that. But, so let's pick a mid-latitude location, 45 degrees north, and show the two lines on top of each other. This looks like pretty good agreement. We have an observation line in black, we have a reanalysis line in red. And you can see when you get big peaks and dips, December 2007, December 2010, they both agree fairly well. And that's what a 0.8, 0.9 correlation looks like when you plot it out on a time series. And so maybe there is agreement between our observations and our reanalysis. And there's a really interesting conclusion to make from this, that the anomalous movement of moisture-taking energy within reanalyses is consistent with satellite observations of Earth's energy balance. I think that's a pretty big conclusion to make out of this, considering how uncertain we are often with reanalysis of moisture-taking energy. But if it closes all together and it meets our top of atmosphere observations of Earth's energy budget, this gives us fairly good confidence in both of these products. There is a tricky point to get across here, that reanalyses are not independent from observations. Many of those micro products do get ingested into your reanalyses, and you get a bit of circular reasoning going on here. But with all the other things that go on in your reanalyses, when you do your moisture-taking energy transport, it equals out to be very similar in your mid-latitudes to your other transport. Yeah.
The anomalies too, but I mean, it shows the conclusion here that the seasonal cycle, that the mean state is just wrong.
The mean state might be wrong. I think that's a key point to get across there. Especially in the northern hemisphere, when you have more land mass, I think that's the biggest uncertainty in your surface heat fluxes, especially your turbulence. Over the ocean, it's pretty more uniform, but you get the heterogeneity of your land, things start going crazy. So that's the mean state, northern hemisphere, might be the problem there.
So does that mean the analysis increment is small compared to the overall fluxes? Is that right? There's like the tendency that comes because of data assimilation, and so that is small, I guess, compared to the overall fluxes?
More from the observation perspective, that we observe northern hemisphere fluxes over land incorrectly, or we have more uncertainty of land fluxes in the northern hemisphere. There's more land, there's more uncertainty.
Okay.
Whereas in the Southern Ocean, there's lots of ocean,
well.
and so we're better at, maybe it's more uniform across the Southern Ocean, so we get those fluxes a bit better than in the northern hemisphere.
Okay, I was just asking, this agreement has to do with the analysis increment being small compared to the overall fluxes.
And the reanalysis?
Right? That would have to be the case, right? 'Cause-
The increment. I don't quite understand your question.
Okay.
We come back to that.
Yeah.
And just to finish this off, we can look at some of these extremes. December 2010, what causes this transport? And when you plug them all out, you can see here, between 30 and 60 degrees north for this month, there is increased transport across all products. This looks like agreement to me. It's pretty good agreement that everything says, for this month, there's a lot more transport in the northern hemisphere. When you plot out your energy budget, you can see this. This is the anomaly of energy budget, an increased gradient. Of course, you increase your gradient. When you take the integral, you must send more heat. And it's to do with this gradient. You have a lot more latent heat in the atmosphere at 35 degrees north and more latent cooling in the atmosphere. And the same with radiation and sensible heat. And so what's going on? What's causing these increased zonal gradients of heat? When you plot out your maps, radiation is a bit spotty. There's maybe an ENSO signal going on. But in your turbulent heat fluxes, you have this North Atlantic signal going on. And for those of you who are oceanographers, this looks like the North Atlantic Oscillation. You have this big latent heat flux into the atmosphere off the east coast of the US. You have this latent heat flux out of the atmosphere into the ocean over the south of Greenland. And it turns out December 2010 was a pretty big NAO negative anomaly. And it comes out to an ocean, a sea surface temperature gradient as well, where you have lots of heat flux coming out of the ocean. You decrease your sea surface temperatures, and over Greenland, when you increase how much heat is going into the surface, so out of the atmosphere into the ocean, you get warmer temperatures. And so it's looking like the NAO creates this zonal gradient of energy that can enforce, when you take the zonal mean and look at how much energy is being sent poleward for those months, you get this increased gradient of atmospheric heating. The NAO is not a measure of poleward heat transport, but why does this connect to each other? Yeah, it's just because it enacts the zonal gradient of atmospheric heating. That's the big point here. What causes a zonal gradient in atmospheric heating? And that comes through as an anomaly of your atmospheric heat transport. You can also do it in the opposite direction. In December 2007, a big negative anomaly was also a positive anomaly in the NAO, when you get reduced latent heat fluxes out of the ocean, but increased latent heat fluxes out of the ocean over Greenland. That enforces a big negative anomaly across all products. We'll skip through this one, we don't need to show that. But yeah, the important point, the tendency is not observed well. And so all products used here have the same tendency from aerified. It's not independent. And so one thing to look at in the future is how much of this variance in the agreement comes from the fact that we have the same atmospheric energy tendency across all products. And that's a hard thing to get into because we don't have independent observations of our tendency.
I would think the tendency is observed pretty well because you have column water vapor and temperature doesn't contribute too much to the variations, right? So
Temperature does. Changes in temperature over a season. You go through big temperature variation, but that could be part of the point of how well can we get the zonal mean tendency. And so we will be looking into that.
okay.
Yeah, there's
I
no
would
products
think-
at the moment
I would
that
think
provide
the
that.
tendency is a lot better than like those surface fluxes, for example.
Yeah.
Because that's something that we actually, yeah. Maybe I'm missing something.
Yeah, plenty of work. And one of those is, can we get an independent observation of that tendency, which is, we will try and do that. The point is that this hasn't been done before, and so no one has tried to get an observation of the tendency. I think that's an important point. There's no product at the moment that provides a tendency suitable to accompany these observations because no one has tried to do this observation. They do it with the UV analyses and do the movement and moisture energy, but there aren't anyone who does it from this energy perspective. And so developing these products that we've identified is a key point of that. So we'll close it up there, 5 minutes left. If there's any questions, we're over, lots of material. Rudra.
So I have a follow-up question. Oh, sorry.
Yep.
Amazing talk, Hamish. I have a follow-up question to what Dan asked you about the land and ocean contrast.
Yep.
And I was wondering that one advantage of land might be more observational data coming from land because you can actually have observations. Do you think any of this data set include that somehow, or there's no way to include that
Well,
in your...
the products try to, but the big point is that there's a lot more heterogeneity in your land heat fluxes. And so even if you do have a single point eddy covariance tower in the north of Wisconsin, southern Wisconsin has a completely different eddy covariance.
So it's not dense enough. The network wouldn't be dense enough that it would provide you a...
Yeah, there's too much gradients over small, whereas over the ocean you have a much more large swath of consistent heat fluxes. So yeah, the fact that the northern hemisphere has a lot more land could be the answer of why we see such a disagreement in the northern hemisphere. That southern hemisphere in the mean state we get quite well, northern hemisphere maybe we don't get it quite well. But you saw in the time series, 45 degrees north was pretty good, and so the enormous variation of these plots go well, but in the mean state they're not the same. Yes. So we'll go in.
Just a clarification question. These observational products, are they using different instrumentation, or are they all?
That's a good point. Very similar. There's only so many satellites you can choose from,
Yeah.
and so a lot of them do use very similar satellite products. Some of them do different things with the way they include it, the way they include buoy data as well, and surface observations. They do things a little differently between them. But yeah, there's only so many satellites you can choose from. That's a good point. So yeah, they're not independent either. So there's a lot of things that aren't independent here. Yeah.
For the Antarctic heat sink concept, it sounds like you're suggesting that maybe the wind stress curl over the last 20 years has pushed ice offshore a bit, and that changes it right along the coast so that more emission can occur. Can you reduce the heat sink if somehow the ice is tucked in closer? I don't know.
Yeah, it's an ocean circulation question. I don't know if that's
No, I don't know about
changing
that.
over time. But the ocean is taking up heat. So the available heat at the surface is being taken down into the ocean and stored away. So it's not being emitted from around Antarctica. Is that key point there. But in terms of how that's changing over time, it's a question for an oceanographer.
Great talk. I enjoyed it, all the graphics and the whole topic area. As I said during Emily's talk, I love a good energy budget. So, yeah, I guess one thing I'm still confused about, so to me, a reanalysis is intended to predict temperature and moisture and provide good records of that. So I'm just curious if you could comment on why you think that you can create a product that does better than that.
It's not that we can create a product. So where this comes from is we want to observe. So if you go back to my first half of the talk, we talked about changes in the top of atmosphere, and the question from the reviewer was, can you look at the atmospheric heat transport into that region? We could just go to reanalysis and say, this is the truth, and put that in with our observations, but that causes this difference. The first half of the talk was all observations. We avoided reanalysis for a purpose. We don't want to include that because we know there are certain errors in it, and so the question is, can you do the other half of that balance with observations?
Okay, so you're going to solve for the transports as a residual. You're going to use the tendency, because that's what I have always done in the tropics for these kinds of
Yes.
things as the best
And that's
method.
what everyone does, but we want to say, can you solve it directly?
Sorry, I thought you mentioned you were going to create a tendency product.
So that's the goal. At the moment, we use a tendency from the reanalyses. We want to be able to use a tendency from observations, but we aren't using that yet. We use the tendency from the reanalysis. We use the boundary fluxes. And if you know the boundary fluxes, you can get how much transport goes in the middle.
So why would you think that the reanalysis isn't kind of the best tendency estimate that
Well,
you
it
can
might
get?
be, but no one's shown that.
Okay.
That hasn't been shown before. Like I showed on a few pots ago, Tyler Cox looked at the trends in these observations, and they're different. And we don't know exactly why they're different. And it'd be great to put an observation plot onto that graph. This one here.
But I assume the reanalysis here isn't solving for the transports as a residual.
It's solving it
It's-
for the moist static energy transport, the dynamic
It's actually
perspective.
calculating the moist static energy budget.
Yep.
So what happens if you just use, I mean, I guess the question would be like, what happens if you just like calculate, I mean, I can talk with you about this
Yeah.
afterwards, I don't want to take up all the question
Yeah,
time.
you get the same answer. If it's
Oh, really?
everything from the reanalysis is consistent with the reanalyses, and we've shown that. So these
Even in the
trends-
tropics.
even in the tropics, the reanalysis tends to be consistent with itself.
There's a question online from Evan. He says, I wonder how shallow bathtub energy sink would change based on your definition of polar. You're leaving out most of the North Atlantic where the majority of the ocean heat subduction is occurring. Would the inclusion of the North Atlantic lead to more parity between heat storage in the northern and southern hemisphere? Or is one hemisphere still doing more of the heat storage work?
I would say the Southern Ocean is still vastly more important than if we did include that North Atlantic ice-free area. It's a good point, and we leave that out for a reason because it's quite a different environmental setup when you include that area. And so we do leave that out on purpose. But I have shown it, if you read the paper even, if I look at different areas, I increase this area out to about 50 to 45 degrees north, and you still have that same balance if you do include those areas of the ocean. It does decrease, and so of course you get more overturning of the North Atlantic when you dive down into that North Atlantic basin, but yeah, certainly this concept holds up pretty well if you just look at the Arctic. One more question, we're a little over time. Anyone else? Sweet, thanks for coming.